Hi, and welcome to my talk tonight on 224 gig SerDes, the next big step in data rates. My name's Clint Walker. I'm Vice President of Marketing at Alphawave IP. Alphawave IP, we provide our customers connectivity solutions, such as 1 to 112 gig PAM4 SerDes, supporting PAM4 and NRZ, and guided I/O for chiplets, PCI Express, IP, and different types of connectivity solutions. Before working at Alphawave IP, I worked at Intel for 22 years, where I focused on high-speed I/O, system and circuit architecture. In today's talk, I'll be talking about mega trends driving connectivity growth in data centers and requiring more and more connectivity solutions at higher and higher data rates. Give you a brief introduction of what a high-speed SerDes is, and then go into the challenge of scaling high-speed SerDes to the next big step of 224 gigabit per second links. And then I'll go through some of the conclusions and predictions for where 224 gig SerDes will end up in a couple of years. So first, some of the mega trends. So cloud migration, everybody knows about cloud market of moving a lot of the data centers up into the cloud. I live in Oregon and by the Columbia River, and you have a bunch of big data centers being put up there for that low cost electricity is coming up. And that's going to grow to about $1 trillion by 2025. Solid state storage has 870 billion gigabytes of flash memory consumption by 2024. Network and compute, you see a lot of the ports and network compute moving from 400 to 800 gigabit ports. And then artificial intelligence, a whole new economy of multi-layered complex usage for machine learning and CPUs, GPUs, FPGAs, and ASICs. All of them will be driving lower and lower cost, faster speeds, and lower power. So for data center connectivity solutions, there's a big growing demand for enterprise grade and consumer cloud services. You can see that it's going to be growing from about $500 billion a year at 14% by 2025 to over $1 trillion. And the increasing number of and size of data centers requires reliable high-speed wired connectivity. So all those different servers in the room connecting together through a network of wired connectivity. So there's a number of data centers that are greater than 15,000 square feet, are growing from 1,579 to 1,849 in 2024. And the number of data center versus cloud servers are expected to grow over the next 5 years. So this is looking at cloud versus legacy enterprise data centers, and they're growing by about 14%, where 2025, the vast majority of them will be cloud servers. And these hyperscale data center operators are relying more and more on third-party IP silicon to ensure the silicon matches or exceeds the performance of merchant silicon. And that's where Alphawave IP solutions are coming in to the cloud and providing them solutions such as our Pipe Core, which is a Gen 1 through Gen 6 PCI Express solution, delivering high bandwidth computing and storage interfaces. And our Alpha Core, our flagship 1 to 112 gig PAM4 and NRZ SerDes, which is register configurable DSP SerDes architecture. Both of those IPs are being used more and more by different types of hyperscale type customers that are going to be growing their data centers and so servicing all the growing demand for enterprise grade and consumer cloud servers in the future. Another wing of this is the artificial intelligence. This is a new generation of data that is growing really fast, and it's growing by these three main drivers. One is proliferation of hyperscale data centers, improvements in hardware and semiconductor technology, and maturing of the software framework. So all this needs to be able to work with software for these new type of workloads that they're doing with AI machines and machine learning. And you see that in 2019, there's about $12 billion in market of silicon containing AI functionality, and that's growing over 29% CAGR. So in 2024, it'll be around $43.9 billion. And challenges arise from AI models becoming more complex and multi-layered. So increased consumption on compute storage and network resources require a large number of interconnected computer nodes. So in these AI, they have these big matrices that are moving around to different chips, even on the same platform and in server racks. And all that data has got to be moved around all over the place. And that's where you need more and more bandwidth for really high-end SerDes. So at Alphawave IP, we have solutions for this as well. Our Zeus Core, another 1 to 112 gig PAM4 and NRZ SerDes, includes a most likely sequence detector. It's a more sophisticated DSP architecture to get more and more reach with those type of applications, and allows for AI where it might be able to need to be able to use more custom solutions instead of following just a standard type of thing like PCI Express or Ethernet. And then on the other side of that is a really low powered type of IO. As features continue to scale and the price of new wafers gets more expensive and more expensive for new mask sets, you see a lot of people moving to chiplets. Chiplets are really a new way to extend Moore's law with more advanced packaging technologies, where you're putting multiple different chips on the same package and using an IP like our Aries core die, which is a high speed, low power architecture, and it's a parallel interface. So instead of being a SerDes, it's parallel, and it would be supporting industry standards like bunch of wires and open HBI, which allow, these new standards will allow different chiplets to be put together and enable high density die-to-die connectivity solutions, deliver a high speed analog front end, allowing signals to transfer across chiplets with very low power consumption. So when we start to look at 224 gig and what's really driving the need for going to the next generation from 100 gig up to 224 gig, there's a 32% 100 gig port count CAGR in global switching, 2x the PC input output bandwidth every 3 years. And the size of the global data sphere will grow from 75 zettabytes today up to over 175 zettabytes over the next 5 years. A zettabyte is a lot of data. And so all that data needs to be moved around for everybody taking their Facebook, their Instagram, posting stuff there, posting videos to YouTube. All that data needs to be moved around faster and faster to continue to grow with how much data is going to be out there. So Ethernet's quickly transitioning up to 800 gigabit ports. So on the front panel of all these data centers, you can see in 2020, most of them are 100 gig ports. By 2025, you can see how much that grows to 800 gigabit per second ports on the front of all those panels. And that'll be comprised of 100 gig and 200 gig SerDes. 100 gig SerDes is getting close to becoming a ratified standard in 802.3. And you can see in this plot here how this has transitioned over the years. 100 gigabit Ethernet started out with 10 different lanes of 10 gigabit Ethernet, 10 gigabit per second lanes. And then that quickly came down to 4 lanes. And so 4 lanes at 25 gigahertz. For 400 gigabit Ethernet, it's going to come down. It started out with bunches of lanes of 25 gig SerDes. And now with the 802.3 CK standard coming out, that'd be 4 lanes at 100 gig. 800 gig ports will start out being 8 lanes of 100 gig, and then quickly transition down to 4 lanes at 224 gig. And you can see over in the last plot of how many design starts will be growing quickly for 224 gig. By 2024, there'll be close to 100 design starts. And what a design start is different chips being made by different companies to support 224 gigabits per lane. So that was a little bit about what trends are driving the need for 224 gig in the market. Next, I'll give you a brief introduction of what a high-speed SerDes is. On silicon, you can print a whole bunch of really narrow lanes, and so you can really run lower frequencies, but a really wide bus. But to get that off a package, you need to have a reasonable number of pins or balls on the package to get that data off. And so you take that really wide parallel data that's on an SoC or an ASIC, and you take that parallel data and serialize it. And so that's the first stop on a SerDes, is to serialize that data and then drive it out. So now you're going to move from the digital land to analog. And so you have to drive out different voltages on here. And the transmitter's job is to start to equalize out and provide compensation for the channel loss that's going to happen when it goes through your channel or your medium. And so this applies delay and inversion followed by add back in and equalization. And what that does is emphasizes the high frequency data and de-emphasizes the low frequency data, so you can start to equalize out for channel loss. The channels consist of the package that the silicon goes in, sockets, printed circuit boards, cables, connectors, all the stuff it takes to link one piece of silicon to another and start to move data from one point to another in a data center and from your house through the internet, all over the place. And so the channel is the medium that's moving across. The receiver is really where a lot of the fun happens for a designer. Receiver overcomes those high frequency losses through a transmission channel by function as a bandpass filter. So it's boosting the high frequency data and de-emphasizing the low frequency data so that you can use complicated DSP algorithms in modern 100 gig PAM4 SerDes to re-equalize that data, because the eye of the data coming in, the waveform you'd see would be closed if you didn't have the receiver equalization. And now that serial data then gets parallelized. So now you have a serial link in and parallel back to the rest of the ASIC or the SoC. And so that's kind of in a quick high level introduction of what a high speed SerDes does. It takes that parallel data, serializes it, does some preconditioning of it. Encoding is another important thing that happens in here, so that you can do some far end error correction. Goes through a channel and then to the receiver, gets equalized, and then put back into parallel, so that now the other side can do something useful with the information and do something smart for the user. So we'll look at approaches for enabling long reach 224 gigabit per second links. First thing we talked about when we're going over what a SerDes link is the channels. And this is showing you an example of today's 30 millimeter packages at 28 gigahertz. So for 112 gig PAM4, the fundamental frequency that you're transmitting data across is 28 gigahertz. In that case, the packages are taking almost up to 6 dB of the channel loss. And this is a VSR loss budget. And so that leaves about going from 6 dB to 16 dB, about 10 dB of loss for the channel to connect the two packages together. And the loss of 20 gigahertz for Magtron 6 is about 5 inches. If you go to Magtron 7, you're about 10 inches. So you get about 10 inches of length between the packages, two devices. Of course, there's other mediums. You can use cables. Going to the front panel, we're going to get 2 meters to 3 meters of loss and get channels up to 36 dB. But looking at how this channel scales from 112 gig to 224 gig, if you don't do anything to help it, is that the package starts to take up a lot of the loss budget. It would double from 6 dB to 12 dB. And that only leaves about 1.2 inches of useful length if you're using Magtron 7. And so putting two circuits or two chips next to each other, they're only 1.2 inches apart, isn't a very useful amount of distance to put two chips apart from each other. And so one of the first things that are going to have to be addressed in moving to 224 gig is the channel loss budget. And so you have to see improvements in the industry for packaging and the channels that it's going through. And for the channels it's going through, might be flyover cables, more use of cables. Cables have a lower loss per unit length. that then do Megtron 6 and Megtron 7. Next thing to look at is what are the different type of modulation schemes we can use. On the far left, we can see here is 2PAM, which is also referred to a lot as NRZ. And so NRZ technology has been around and very popular. It's been used in Ethernet up to 25 gig, PCI Express up to Gen 5 is NRZ. And you can see here, when you're sending is 1 bit of data per UI. And the UI is from this cross point to the other. And in this data, we're either sending a 0 or a 1. When we move to 56 gig in Ethernet, and pretty soon that's coming out in PCI Express Gen 6 as they move to PAM4. So with PAM4, you're sending 2 bits of data per UI. So once again, you can see where the UI is. And in here, we're sending either a 00, a 10, 01, or a 11. So there's 2 bits of data that's transferred in each UI. Now, the thing to notice with this is how much smaller each one of these levels get between having a 00 or a 10. It's been cut in by 30%. So if this was, assuming they're all sending the same voltage swing from the mid voltage to the max, here you lose about a third of your swing where you have to decide if it's what bits you're sending. And PAM4 is being used today in 112 gig PAM4 SerDes. And the next step up from that would be PAM8. In PAM8, you can see there's 8 levels here and how much smaller each one of those levels gets. And moving from PAM4 to PAM8 does not double the number of bits. It's only 1 more bit that you're sending per UI. So you can see here we're sending a 00 or 11. Here you'd be sending a 000 or 010, only 3 bits of data. To really double the payload, you have to move to PAM16 to send out 4 bits of information in 1 UI. And that even gets the signal even smaller. And so when you're comparing the different PAM modulations of 2PAM, 4PAM, 6, and 8, you can see how compared to PAM4, how much more extra bandwidth you need in the channel. So if we were to do a 224 gig at PAM2, you need almost 300% more bandwidth. Moving to PAM6, you only need 55% of the bandwidth, and PAM8, you only need 33%. And so the channels we're looking at in the previous slide, the higher the modulation you need, the lower the fundamental frequency of the channels are, and you can get longer channels and more useful channels out of that. But there's always a trade-off for doing something like that. And you can see when we moved from NRZ or PAM2 to PAM4, we lost about 9.5 dB of signal to noise ratio. And that's what we're seeing up here. We're getting 1/3 of the height. And when you change that to an SNR, you're losing 9.5 dB. And for PAM4, you know, we have that working today in the industry. 112 gig SerDes are working really well with our Zeus core. We're doing over 45 dB of loss with that. When you move to PAM6 and PAM8, you can see, you know, the signal noise ratio that you're losing by those higher modulations gets worse and worse. So this is the trade-off of moving to higher type of modulation. Now, we have a couple other on here. I'll point out 16 QAM, so quadrature amplitude modulation. So up here you can see in this case, we have 16 different constellations that we can land on. And so this will be sending 4 bits of data per UI. But to get QAM to work, you need you know, quite a bit more bandwidth and carrier frequencies. And so this one we won't really look at too much, but it's just put on here so you can see relatively other types of options that you could do. And it's really the constellation spacing for this is the same as PAM4, but you need to have a carrier frequency equivalent to or greater to the signal bandwidth to combine in-phase and quadrature signals. They require twice the channel capacity compared to PAM standards. A more advanced technique is a most likelihood sequence detector, so MLSD. This uses energy in ISI to boost signal power rather than just remove it like a DFE. So in a DFE, you're actually taking information out of the channel. Here you use it to help predict what the signal should have been. So it detects a symbol sequence exhaustively over all possibilities and looks for the root summed error that is the smallest, and that ends up being the correct sequence of bits that should have come out. So it actually looks at, if I had this sequence of bits and compares that to what it had received, and until that root sum error is minimized, then you know that you have what the signal was. So the blue waveform in here is a received signal, and the other one is the most likely sequence detector guess. So it's saying, here's what the channel should be. If we had this channel, what would it be? And so like here you can see the difference between the blue and the yellow has an error of 0.3. Here they match really well. There's still some error, but you minimize that error. And so this is the type of advanced signaling techniques that we can use in DSPs going forward. And it's really what I'm seeing in the industry now is moving from analog architectures to DSP-based ones. They are scaling with future processes that you're getting from the fabs as they shrink and shrink to smaller and smaller lithography nodes. You start to get a lot of benefits in power and area using more and more DSP technology. So here's an example of a 200 gig channel. Channels 1 through 3 are examples of chip to module applications, and you see they're varying from 7.4 up to 18 dB of loss. Channels 4 through 6 are representing 200 gig cable assembly. So here we're getting much longer reaches to 1.5 or 2 meters, and the loss is going all the way up to 38.6 dB. And you see there's a pretty wide range of insertion loss deviation, and the frequency we're going up to is all the way up to 100 gigs. So looking at 50 to 60 gigahertz, you can start to see some of these channels drop off, and that's where we'll need some improvements from that. So here's some results from a 200 gig bandwidth requirements for bit true modeling. So this is actual modeling of our architecture that we're designing for 224 gig SerDes. And what it's showing is the target bit error rate can be met by scaling bandwidth only 1.6x compared to 100 gig transceivers. And even channels 5 and 6 having over 30 dB of loss are showing acceptable bit error rates at 1.6x the bandwidth. Today for 112 gigabits per second, your minimum bit error rate is 1e-4, which would be this line here. But really what you want is a couple orders of magnitude of margin over that. And so we'd be looking at 1e-6 to find a good solution for that, and all the way up to 1.6x the bandwidth. So we don't actually have to double the bandwidth compared to 100 gig to get these 224 gig channels to work. So in conclusion, an explosion in data is really driving speeds, the need for speeds to scale from 112 gig to 224 gig. People are not going to stop YouTubing. They're not going to stop Netflix binging, and the need for continuing to make data rates faster and faster and lower the power of that will continue to drive us to 224 gig. And 224 gig long reach electrical transmissions are achievable. PAM4 is preferred, but may not support some of the longer channels. If the channels are able to improve, then we can support them with PAM4. But PAM6, based off their SNR, is a good alternative for physically longer electrical cables. So if we can avoid having to go to optic channels everywhere or having active electrical cables, PAM6 may be a good balance for that. We are seeing more and more momentum though with PAM4 only solutions, and those will be the first ones with optical links driving up to 224 gig. And with optical links, you can have a shorter chip to chip or chip to module type link for that. And so in the end, modulation schemes may end up varying across different form factors. If you need to get a longer cable to work, there may be PAM6 in the industry. Improvements in channels and DSP architectures and coding will all be needed to reach the next big step in data rates. But the bottom line conclusion is 224 gig electrical links look very achievable, and we'll start to see them enabling 800 gig ports in the next few years in the industry. Thanks for listening to my presentation today, and I think now we'll take some Q&A. Thank you.